So we were discussing. So we were discussing instruction architecture. Finish. 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 Pause. Okay, so we have discussed different kinds of processor, and they have the hardware features, and they have correspondingly they have instruction set. So this is the overall one human concept where the data and program is stored inside the memory and different locations. So we have another model like Harvard architecture where data and instructions are stored in separate memory, right? So and we have the functions of data path and control path and role of ALU and the functions of a control unit. We discussed here to control the data path, movement of data within the data path, executions, bus transfer, data transfer, etc. And there are different types of memory, primary, secondary, and we have magnetic disk and flash memory also these days. And input output unit we discussed. Then instruction set architecture, how it is, why it's important, right? It's a view, programmers view, how programmers view the functionalities of a processor, and how we can utilize this structure, hardware structure or units. Okay, they have a different instruction set like we can have load, store, add, sub, all those based on the whatever hardware designed by the processor designer or computer architect. Okay, so what are the factors which depends upon the instruction formats? Number of bits per instruction. Basically, this is depending upon how much data storage capacity is there, and location. Where are you taking the data from memory, from registers, from different locations? And we can have data register to register, memory to memory operations, and different types of operands. We can have immediate addressing. That means we can directly have the data add immediately 5, or we have data within memory add m. That means m corresponds to memory, or add register. That is add r1, r2, something like that. So we have different kinds of operands called addressing modes, and we have different types of operations also. So other important things are amount of space the program requires, instruction complexity, instruction length, and total number of instructions also. Instruction length and these other factors. Instruction length. The instruction length also depends how much bits you are planning to put in one instruction, and what kind of memory, number of operands, addressable registers, etc. Instruction formats. So these are the different architectures we are discussing. So stack. This is stack architecture where all the data inputs are coming from stack and output is also going to stack. So whatever process we need to do, we do input into the stack. The result is also updated within the stack. We can see the stack architecture. So based on the hardware architecture we have, your instruction set is also defined. Number of bits, where the inputs are coming from, where the output is coming from, right? All those processing. Now this is accumulator based. Like in Littleman, we have this kind of things. We have accumulator is taking one input, and another input is coming from the memory, and after the operation, the result is again going back to the accumulator. So you can see the instruction set is based on this load X. That means loading the operand from the memory location X. Add Y. Whatever already in the accumulator is added by the added with the data stored in the location Y. Then it is stored to Z. That means the result is already in the accumulator and it will be stored into the Z location. So this is register memory. So one input is coming from register, other input is coming from the memory. Result is again going back to register. So this is called register memory architecture. Now we need to specify two operands. You can see load R2 X. So one input is coming from R2 and the input is coming from X location. That is memory of X. Then add. We have again adding R2 and Y. Store. Then store again. We have to specify which location we are storing. Okay. So then this is register to register architecture, where both inputs are coming from different registers and output is going to another register. You can see the three add R3, R1, R2. Can to specify three operands. That means you can see the instruction size is increasing. We need to operation and three registers we have to specify. Okay. So first we have to input this numbers into the registers. Then just take the addition operation and again store into one register. Again store that register into the memory. Okay, so there are special purpose. This is something which we have discussed stopped yesterday. This what is special purpose register? These registers are specially defined for some particular functionality. That means you cannot user may not be able to program it. You cannot use store your data into this register. They are specially functioned. They are you can say application specific. Here it is the application is memory input and output. So this memory address register and memory data register are used for memory operations. That means one is for storing address and there is storing data. So there are two operations, reading and writing. So we know what is reading. Reading is taking something from the memory into the to the user or to the ALU or accumulator. And there is writing, that is whatever in the accumulator or data in the register we have to put into the memory. That is for writing. So memory is always considered a linear array of storage locations, as you have seen in the little man as a mailbox. Okay. So what is MAR, memory address register? What is MDR, memory data register? As the name suggests, we can easily understand as MAR always stores address. MAR always stores address, memory address register. Memory address register. Okay. And MDR means memory data register. So MAR always stores address and MDR always stores data. Okay, so this is a part of processor actually, and they're interfacing with the primary memory. So whichever data from the address, for example, you need to take the data from XYZ. So corresponding that address of the data has to be stored in the MAR, memory address register. And whenever the address register specify that address, and the control unit will tell, okay, I have to read signal is exerted or inserted or actually activated, then the data is going to the MDR. So MDR stores the corresponding data pointed by the MAR. So you can see the MAR is a unidirectional. It always points to the memory, always one way pointing, because address always we need to point into the memory. So whatever address you are accessing, whether reading or writing, will be specified in the MAR and is pointing towards the memory. And that corresponding data, when we are say reading, address pointed by the MAR, corresponding there's a data and that is going to the MDR, right? But this is the case of reading. In the writing case, what happens? MAR points to memory. For example, MAR points to memory location 99, and whatever stored in the MDR will be going to that location in the primary memory. That, for example, XYZ, which is stored in the MDR, is going to the 99th location. Okay, so you can see the MDR, the data is bidirectional. Bus is bidirectional. You have to put the data into the memory for storing, as well as or writing, or as well as you have to take out the data from the memory for reading or loading. Okay, so it's bidirectional. Okay, so these are special purpose register. It has special use. So what are the process of reading? Load the memory address into the MAR. This is first operation. First we need to take the address into the MAR, then the control signal. Then what the control signal we specify the read operation. Now as soon as the control unit specify read operation, memory understand that whatever pointed by the MAR, that location data had to send to the MDR. Now the data is read from the memory and stored into the MDR. Okay, so address is in the MAR, then activate signal read, then the data corresponding to that location or address come to the MDR. Now what about the writing? In writing, again, whatever address to which we are writing, it will be pointed by the MAR, load the data to the return to the MDR, right? Then the data, whatever we need to write into that address has to be read by the MDR, and the issue the control signal write. Okay, so this is this process. Okay, now there are other two registers, that is program counter and instruction register. So as we discussed a bit previously, the two in Littleman also we have seen after every operation, Littleman presses a switch. You can see there's a switch like this. When presses the switch, what happens? So it is incremented. Whatever value in that calculator is incremented by one. So what is the idea? The program counter is always holds the memory address of next instruction to be executed. It always guides the little man where my next instruction is going to come from. If there is no such a notepad, which is called program counter, which is can be incremented, little man cannot hold that memory in his own mind. It's very short-term memory person, so it has to written down somewhere. So that is done by the program counter. It always points to the next variable, next instruction to be executed, right? So as soon as one instruction executed, again increment plus switch is pressed, and points to next instruction to be executed. So automatically incremented to the point next instruction when instruction is being executed. Okay. So presently executed instruction is presently executed, but at the same time PC or program counter has to be incremented to pointing to the next location. Now what is instruction register? So instruction register is another register or storage. It temporarily holds an instruction that is fetched from the memory. That means when little man is while executing, it is executing some specific instruction, and that instruction is stored in the instruction register. That means temporary holds an instruction that has been fetched from the memory. So once program counter is telling which location my next instruction is going to come from, right? That instruction, when it is being executed, will be coming to the instruction register, right? So this is the storage of instruction register where my presently executed instruction is stored. Instruction is stored. Program counter stores the address, but instruction register stores the instruction, specific instruction. Okay. So now this instruction, once stored by the instruction register, has to be decoded by the control unit. So it has to know what kind of instruction is this, adding, subtracting, all those things. And it also contains information regarding location of the data, whether it is coming from memory, register, or stack, queue, etc. etc. So these are the other two registers we have discussed: PC, program counter, and instruction register IR. This is very important. This has been asked in a lot of exams for general basic. This is a very basic question. Now, what is architecture? This is a simple example. What are the special registers we'll be using? That is MAR, MDR, which we already discussed. So these are all related to memory operations. MAR is single unidirectional. MDR is bidirectional, and the control unit also need to tell whether it is reading or writing. So this is called control bus. This is called control bus. Control bus, because it carries the control signals: reading, writing, enable, starting, stopping, clock, etc. Here it is reading and writing only because it's memory operations. There are two possibilities. And MAR is called address bus. The data carried from the MAR to the memory location is called address bus because it carries the address information. Maybe multiple bits, maybe 8-bit, 32, 64, depends upon the architecture. And MDR is a bidirectional bus. It's called data bus. It stores the data which is stored, which is to be processed, etc. So data bus ho gaya, control bus, and address bus, right? So you can know the three major types of buses. Similarly, when we insert any device into this USB port or any part of the system, these three buses will be coming to picture. So the device which you are inserted, or the CPU, mouse, or printer, plotter, it needs an address line, a control line, and a data line. So data line to data bus, we transfer data, input or output, and for the control lines, we synchronize input, output, how much I have to print, reading, writing, etc., clocking, and data bus transfer the data, and address bus points to the address location of that device, maybe buffer location or kind of the driver location, etc. All those. We have program counter, instruction register. This is a part of a control unit or control path. Okay, and there are this is general purpose register. You can use it for storage R0, R1 till Rn-1. There are n registers here. Okay, so this is a control signals coming, reading, writing, control signals, and ALUs also there. Okay. So there are some instruction examples. So this, I think, it's not very difficult for you because we discuss this thing. So we shall illustrate the process of instruction execution with the help of following instructions. So add R1 location 1. So you can see the one of, so you are adding two numbers, right? say number 1 and number 2, two numbers. So number 1 is stored in R1, register R1, and second number is coming from location A. Location is A is giving. So this is a memory. Second number is coming from memory location, right? So add the contents of memory location log A, address of memory location A, to the contents of register R1. So this means this can be mnemonic. This is the way we represent this working with instruction. That means the memory data from the memory location A and R2 is added together. Okay, and data is stored in the R1 only. Again, data is again coming back to R1 updated. Another type of instruction is add R1 R2. In previous instruction, you can see the memory location is accessed and register location is accessed. Here, both registers are accessed. R1 and R2 is accessed. So the contents of the R2, add the contents of register R2, the contents of register R1, and result is stored back in R1. Okay. So every instruction has a meaning. That meaning is designed by the or defined by the computer architect. So two processors might have same instruction, but it can be meaning entirely different, right? For example, add R1 R2. I can also define like R2 assigned as R1 plus R2 in one processor after the computer architect. Another processor may be R1, the result may be going to R1. So this can be different. So we have to know the data sheets, what it is meaning to a specific processor. But the more universal, if you need to make a processor which is more universal, should be compatible with the existing architectures. But there is no hard and fast rule. You can design your own instruction set architecture. Now, what are micro instructions? This is a very important part of the micro instructions. Means micro instructions are instruction within instruction. That is micro. There are big instructions like add, subtract, load, store. So by performing those big instructions, there are small micro instructions, small instruction of data transfer, switching happening within the processor. So these are collectively termed as micro instructions, or I can say RTL also, register transfer language. That is register. Data is transferred from register to register. So each of this is represented in micro level using RTL, register transfer language, RTL. Or you can say not only RTL, you can also micro instructions also. So for example, add data from the register R1 and data from memory location log A, result is going to R1. For example, if this is the instruction, let's see what are the micro instructions. So for example, here we assume the instruction stored in memory location. This instruction, for example, the whole instruction is stored in the memory location 1000. For example, I'll write the 1000. This instruction is stored. So, so initial value of R1 is assumed as 50. For example, 50, and log A is value is 5000. So what is the meaning of this? Value 50 should be added with the value stored in the location A, that is 5000's location, and the result is going to R1 only according to our definition. Okay, so before the instruction executed, PC contains the value 1000 because this is the location where I am going to answer the instruction from. So the content of PC is transferred to memory address register because I need to take instruction from this location. So MAR should have this value. This is represented by this MAR. PC value is going to MAR. Right? PC means it points to the instruction which is we are going to execute just now, or next instruction which has to be executed. The next instruction is stored in 1000. So PC value has to be given to MAR so that I can access or fetch that instruction from the memory. So the first step is PC value going to MAR. Then when MAR is filled, now the memory should know whether it is reading or writing. So now the control unit will send the request read to the memory unit. So when the read is issued, what happens? That data from that particular location, that is MAR's location, is going to the MDR, memory data register. So instruction is fetched to the MDR. Right? Now the MDR has the instruction which we want. Now we need to execute it. For executing, we need to decode it. What is the instruction meaning of this instruction? So this instruction, before going to the control unit or before going to be decoding phase, you need to store it in instruction register IR. So is whatever the instruction stored in the MDR temporarily is going to the instruction register. Instruction register can also be a part of control unit, right? Not a problem. Now the instruction is already in the IR. Now it will be decoded. It will be going to the control unit, and control will be decoding, and control signals will be generated. But at the same time, now next PC should point to the next instruction. So immediately my PC is incremented to point to the next instruction. Okay. At the same time, the present instruction, which is in IR, is decoded and executed by the control unit. Okay. So this is add operation. Opcode is add opcode, and the first data is coming from R1 location register. Second data is stored in the 5000 location in the memory. So there's a memory operation here. The memory has to take that value, and this value has to be added to R1 plus that value from the location 5000. So like this, the result is going back to R1. Same time, we can say PC is point to PC assigned as PC plus 1 incremented next instruction is pointing to next instruction. Now let's again discuss location A in previous example is 5000, and which is transferred. The data stored in 5000 location is transferred from instruction register. So I think we are discussing load operation or something. Let's see. Okay, this is add operation, micro instruction. So location A 5000 is transferred from the IR to the MAR. Okay, now you can see again while executing the instruction, within the add instruction there is a location A. Now location A, we know it is 5000. So again while executing the instruction add, we need again to fetch the memory. Okay, so that is the meaning here. So while it is executed, the location 5000 is transferred to MAR because we need to take the data again for addition. So the data in the 5000 has to be retrieved. So 5000 has to go to the MAR pointer. MAR is pointing to the MAR. The data from the IR operand. Here operand. What is operation? Operand location A. This is the operand, and this is nothing but 5000. So the IR, only those part of the operand, that is address, is from the IR is going to the MAR. So that is only what we want to fetch. We don't need to fetch the whole instruction, but we need to fetch that part of the instruction which is going to accept data from the memory. That is 5000's instruction. Now read request is issued by the memory unit, issued to the memory unit by the control unit, and data is fetched to the MDR. Now MDR consists of this data. This is like this: MAR, memory location MAR, that is 5000, is going to MDR. Now MDR has the second number which has to be added. Now we can do R1 assigned as R1 plus MDR. Result is stored in R1. Okay, so overall these are the set of micro instructions we will be using here. So you have to understand why this is micro instructions, how it is written. So first is fetching, that is PC value is going to MAR. Now instruction has to fetch, that means corresponding value value stored in the location pointed by the MAR is going to the MDR. Then MDR instruction is in MDR, so instruction is going to instruction register before decoding. So that's done. Then parallelly I had to increment the PC, so pointing to next instruction. Then our add instruction has another operand which points to the memory. Second number is already in the memory. First number in the register, second number is in memory. Again accessing that. That is again in the instruction register. There is some part of the instruction which is calling from the memory again. So IR operand is again going to memory address register. So once memory register pointed to that address, memory address register, in that location there is a data that is going to MDR. Now MDR has a second number, so now we can add R1 assigned as R1 plus MDR. So this completes the add instruction. What is the instruction executed? Add one register and location A. So this corresponds to a number location that is 5000. So while even the instruction itself has a location that is 1000. Initially we have to accept that PC is going to MIR, then the whole instruction is going to IR. Then that part of the instruction, that is location A, again has to, we have to fetch that data or instruction stored in this location. So that is done here. MIR showing the IR operand. Then this is already in MDR. Once in MDR, it can be used for addition. And the result is already stored in the calculator screen or accumulator. Okay, this is another instruction example. Here we have a register operation. Initially, we have one register operation, another memory operation. Here there are two register operations. Let's see how it works. So instruction stored in the memory location is 15. So this instruction is stored in location 1500. Okay, so instruction is this. Now the initial value of R1 is 50. So R1 is already storing some value 50, and R2 is already storing some value 200. So before instruction executed, PC contains 1500, right? Because PC is pointing to the next instruction or presently executed instruction. So it is 1500. Now content of PC is transferred to MAR. Now I need to fetch that instruction, right? So PC is going to MAR. The read request is issued by the issued to the memory unit by the control unit. So reading the specific instruction stored in the location PC, which is initially given to the MAR. Now that instruction is nothing but add R1 R2. Okay, so this instruction is fetched to the MDR. Initially, this instruction stored in the MAR location, pointed by the MAR location going to MDR. So this is in MDR. So instruction is fetched to the MDR. Content of MDR is transferred to IR. So this is the instruction. So this has to go to IR register. Now the PC is incremented, point to the next instruction. Okay, as soon as PC is free, it can use for next incrementing, pointing to next instruction to be executed. The instruction decoded by the control unit. Now the control unit, no, this is R1 SNS R1 plus R2. So it takes the data from R1, takes the data from R2, enable the registers, open the data to pass to the ALU, and from ALU it triggers the addition operation. After doing addition, the result is again stored in R1. So R2 is added to R1, result is stored in R1. So this is the overall, you can say the micro instructions or RTL of the instruction add R1 comma R2. Okay, I'll repeat again. When you have instruction, it will be stored in some kind of memory in the memory. So first you need to access that. So first our PC will be pointing to MAR, then MAR, whatever data stored in that location is going to MDR. Now from the MDR, there is an instruction, so it is to go to IR. So from IR, the control unit will be understanding, okay, this is for addition. So the data is coming from R1 and R2. So once control unit understands this thing, it will execute this instruction in the ALU or signals the ALU to do this instruction. At the same time, PC can be incremented, it is free. It has to point to next instruction. Right. This is important, as PC update is important as early as possible so that we can prepare for the next instruction. A lot of intelligent algorithms which prefetches, which predicts all those things. So this is possible if you already know what is next instruction. So it is interesting problem. Okay, so that's all for today. So in next class, I think we'll discuss the Mary computer. So in Mary, you can see there are a simple architecture. So this is the Mary architecture, very simple. All those what we discussed is already here. It consists of everything. This is the most simplest because Littleman was a conceptual thing. It is a conceptual thing which doesn't have hardware significance. So control unit is Littleman, calculator is ALU, mailboxes. So, but this is Mary is the most simplest basic thing with all the minimum features like MBR is the MAR is the pointing to the memory, and input register, output register, in basket and out basket is the ALU, calculator screen is the calculator screen is the accumulator. ALU is the whole calculator, and PC is also the instruction register is also everything is there. So we can model this also. This is the complete CPU, control unit, data path, That's it. So this is the controller, and memory test access memory also. Right, and its memory address varies from the Littleman. The difference is in Littleman only 100 locations. Here it may be more locations are there. But the overall architecture remains same. But this Mary is completely hardware. You can correlate every feature of Mary into the real hardware. And you can design it, you can code it, you can do it, model it, you can work on it. So this is the advantage of Mary architecture. More seamless architecture you can see of exactly of Littleman. But branching instruction, I think there is one special branching instruction. That is only difference. So these are the features. So this is already we have discussed. Registers we have discussed till now is these are the registers we have discussed. So first thing is accumulator. So accumulator we know the data, one data which has to be operated. That is addition, subtraction, multiplication, whatever. One data is coming from accumulator register, right? And the result is also coming back to the accumulator. And this is the same case for microprocessor also. This name nomenclature terminology is same, exactly same. Almost all the processors, this kind of concept is also used. And memory address register, we know memory address register holds the address of the referred data or reference data. MBR stores the memory buffer register, it holds either data just read or written to the memory. So both, even writing and reading also, we use MBR. The PC, we already know if hold the address of the next instruction to be executed. IR instruction register, which holds the next instruction. That is, this holds the instruction itself. This holds the instruction to be executed. Right. This is IR. And intrage and outrage is used for this in basket and out basket. Those input values to the system is passing through the in register, and those things which the system or the computer Mary has to output is going to out register. It has some kind of fixed storage, maybe 16-bit, 32-bit kind of thing. I think here it is 8-bit, I'm not sure. No, yeah, here it is 16-bit, I think. In register also 16-bit, out register also 16-bit, maybe. Okay, then we have to know what is the size of our instruction. So these things, how many bits, 16-bit, 32-bit, 8-bit. So in instruction, we know an instruction has to be some specific bits. For example, we have say 16 bits. So with 16 bits, we have to decide how many bits will be opcode, operation code. That means it depends on how many operations we are planning. Addition, subtraction, multiplication, division, logical operation, etc. That comes opcode. And there is operand, how many bit size you are giving. So that much bit size I can access the memory. For example, it is 8 bits, so how many memory locations I can access? 2 raised to 8 locations. If it is 10 bit, I can access 2 raised to 10 locations. You can also specify the register destination register, where my data is coming from, where my data is going, etc. That's also for memory addressing, register addressing. So there are some instruction which doesn't have opcode. It can have opcode but doesn't have operand. For example, halt, stop. This instruction doesn't have an opcode. It doesn't have to work on data. Okay. So there are some. It's called machine control instruction. Machine control instructions. So there are a lot of instruction like that. So then we specify how many bits our instruction should be having, and in that bits, 3 bits or 4 bits should be opcode. Some should be the address, and that address bits decides how many location I can access. For example, here 12, 0 to 11, 12 bits. So 12 bits I can access 2 raised to 12 different locations. Okay, for example, and for example, is given add 259. Right, so this is written like this. 3 stands for addition, and 259 is 259. So that is memory location. So whatever data in memory location 251 is added with the value in the calculator, and result is going back to the accumulator or calculator. I think I'll stop it here. If any doubts you can ask.